Okay, today I'm going to describe some really big picture trends in standing forest biomass. I'll talk about both the magnitude and spatial distribution. First, I'll be talking about a really large 8-state area, all forest types lumped together, and then I'll focus in on a few specific forest types, including pinyon and juniper forests, lodgepole pine, and aspen. And again, I'm using the forest inventory and analysis data set from 1980 to 2009. Just a little bit of background about the Forest Inventory and Analysis Program, or FIA. It's a nationwide ongoing inventory. It's broken into 4 geographic regions. Our region is the Interior West. It includes 8 states, and since 2000, we implemented a new sample design that had a total of over 30,000 forested plots in those 8 states. Each plot represents about 6,000 acres across the landscape on a systematic grid, and each plot is inventoried now on a 10-year return cycle. This schematic gives you an idea what a current FIA plot looks like on the ground, just so you have an idea where these data are coming from. Each circle is a subplot. There are 4 subplots per plot. They have a radius of 24 feet. And on those subplots, we record 4 main types of data. First, we have general site and stand characteristics, such as slope, aspect, elevation, forest type, size class, stand age, and several other things. We actually tally every tree larger than 5 inches on each subplot and do sort of the standard suite of forestry measurements. Then we also do understory vegetation data collection, including height, classes, and percent cover. And then we do downwoody debris transects. And I'm not going to talk anymore about the understory vegetation or the downwoody debris transects, but I will point out, if you were here for Justin's talk, you probably noticed that the surface, sort of the forest floor component of biomass, sometimes doubled the total biomass for some forest types. So it's not something we can just ignore, but I'm going to ignore it for a little while. Okay, so for the work that I'm presenting today, I restricted the FIA data set to plots that were sampled at least twice between 1980 and 2009. Within those plots, I only included trees that were at least 5 inches in diameter, either at breast height for timber species or at root collar for woodland species such as pinyon and juniper. Biomass is calculated on a per tree basis in oven dry pounds and then aggregated over the entire plot in oven dry tons per acre. And the specific measurement years varied by state. This map just shows what was left when I restricted the data set to the plots that were measured at least twice. In purple, you can see the pinyon and juniper plots, coniferous forests in blue, broadleaf in red. And I had a pretty big sample size, over 10,000 plots included in the, this big scale comparison. As I said, the measurement years varied by state and often within a state. I wish I could go back to 1980 and beg and plead everyone to please create a balanced sample design, but instead I was learning how to add and subtract in 1980. And now we're doing a more balanced design at this point. As you can see, though, most states were measured pretty continuously in the 1990s and then again in the 2000s. The 2 exceptions there are New Mexico and Wyoming. So when I present my results for specific states, I'll include New Mexico and Wyoming, but keep in mind the time period is slightly different for those states, and I did not include them in large regional trends where I lump the other states together. Okay, so moving on to the actual results and the changes generally from the 1990s to the 2000s. This slide shows the mean biomass in tons per acre for all plots in each state. This chart here at the lower right, this is 6 states, so excluding New Mexico and Wyoming. And as you can see, overall, total biomass has increased, dead biomass has increased, and live has decreased. Big picture trend there, decrease in live biomass. We did see some states that increased the amount of live biomass, such as Arizona, Colorado. And one pattern that's kind of interesting that you see, especially in Idaho and Montana, up here and over here, and somewhat in Utah, is that total biomass either increased or stayed the same, while live biomass decreased. And I'm pointing that trend out because I've actually seen people take forest inventory data and compare live standing biomass and say this is the amount of standing carbon on the forests. And if they do that using only live biomass, they're missing a big part of the picture and sometimes producing erroneous trend lines. This map shows the distribution of total standing biomass in the 2000s, so time 2. The darkest blue areas have more than 60 tons per acre, and as you might expect, those more productive areas are in northern Idaho, western Montana, also some very productive areas in central Colorado and the spine of Utah down to the Mogollon Rim in Arizona. Okay, I'm going to kind of quickly go through a couple side-by-side comparisons. This is live standing biomass, time 1 versus time 2. Again, darker colors represent more biomass per acre. And overall, the two maps look pretty similar. There were some increases down in this area and some decreases. I might need the pointer for this. Decreases in central Idaho and southwestern Montana. Okay, same thing, but this time it's standing dead biomass. Again, darker colors are more biomass per acre. And the first thing I noticed looking at these two maps, in general, time 2 is a lot darker. They're in different classes. Lots of increases in standing dead biomass pretty much throughout the region, where we didn't see big increases in live. These 3 maps just show the change in biomass for the live and dead components, and then again the total. So as I mentioned before, big changes, loss of live biomass, increase in dead biomass in these areas that were likely hit by big wildfires in the early to mid 2000s. We had some insect disturbances going on. And then on the right, that just gives you a general picture of where we saw total increases and where we saw total decreases, as shown in green tones versus yellow and orange. Okay, now I'm going to talk about some specific forest types, starting with pinyon juniper. Then I'll talk briefly about lodgepole and aspen. And I started with such a big sample size, I didn't want to start mixing in states and years and groups that had less than 25 plots per group. So I didn't include any really small subpopulations there. So first I'll talk about pinyon and juniper. As Justin mentioned in the last presentation, FIA breaks pinyon and juniper woodlands into 3 main forest types. The first is Rocky Mountain juniper. That's the least abundant within this 8-state area. It's pretty widespread though, accrues northward into Montana, shown in red here. Juniper woodlands include Utah juniper, one seed, alligator, western juniper, a few others. And by far the most widespread and abundant is the pinyon juniper forest type. And again, that's defined by having not only a pinyon species present, but it has to be successfully regenerating on the site to be that forest type. So if we look at the biomass per plot among those three forest types, you see the Rocky Mountain juniper on average is the most productive, and it also saw the greatest increase from the 1990s to the 2000s. However, all three types did increase. And now, since, as I mentioned, the pinyon juniper forest type is by far the most abundant, I'm going to focus in just on that for a few minutes. This shows state-specific trends as well as the regional average. Again, there was an increase in total live and dead biomass. And that trend was true almost everywhere except in Utah. Notice Utah has the highest mean biomass per acre of those four states, but it also was the only state that had a decrease in live PJ biomass from the 1990s to the 2000s. This graph shows the mean rate of change by the year of the second measurement. So I took the time 2 biomass minus time 1 divided by the number of years, just so I wasn't comparing something that had been measured 5 years later with something that was measured 20 years later. And the main reason I put this up here is to show that the mean increase per year in live biomass was about 1/10 of a ton per acre per year. So absent any major disturbances or stochastic events, over 10 years you might see an increase of 1 ton per acre. And again, this is throughout the entire region, regional averages. This map shows where the most productive PJ plots were. The red dots show the least productive, less than 5 tons per acre. And again, everything is oven dry tons. The darkest blue dots are more than 20 tons per acre. As you can see, if you know the geography of the West, they're sort of centered on the plateaus and mid to high elevation mountain ranges. And this kind of corroborates what Justin showed in terms of his simulated biomass accumulation, is that the biomass per acre is generally highest in that sort of sweet spot at 7,000 to 8,000 feet. One other thing you can see in this graph, the lower bars represent time 1, the upper bars are time 2, green is live biomass, and red is dead biomass. The biggest decreases in live biomass occurred at the highest elevations and the lowest elevations. And between 7,000 and 8,000 feet, on average, there was less change than the other elevation zones. Okay, another way that we can look at some of these trends is by ownership category. On this chart, the left-hand bar in each category is time 1, time 2 is the right hand in each category. And again, remember, we did see a slight decrease overall across the state of Utah in PJ biomass. But if you look at national forest lands, non-national forest and non-BLM lands, this other federal category, and then tribal lands, there's no decrease in the total biomass. And on national forest lands and other federal, we actually saw an increase in live biomass. We saw decreases in total and live biomass on BLM, state and local government lands, and private lands. That might be because of elevational effects, or it could be due to differences in management. And I show this partly, it's kind of interesting, but also to illustrate that depending on the forest type or the specific subpopulation you're interested in, we have the data to drill down and look at some of these patterns. Okay, and now I'm going to zoom back out to some bigger patterns again. Within the state of Utah, I'm going to talk just briefly about individual forest types, the other forest types in Utah. This map shows sort of rough categories of forest types, and the larger dots represent more biomass on a per acre basis. And these are the specific forest types that FIA has inventoried in Utah. Again, the lower bar in each group represents time 1, time 2 is the upper bar. Two things I want to point out here. One, the pinyon juniper component is small on a per acre basis relative to other forest types. And also that almost every forest type has seen an increase in the amount of dead biomass. And a lot of them, even as they saw the increases in the dead, decreases in live. So the growth not keeping up with mortality there. Okay, now I'm going to shift gears back out to the 8-state area and talk about lodgepole pine and aspen real briefly. This map shows the distribution of lodgepole pine plots by productivity class. As you can see, can you see the dots on the map? Is that back pretty well? Okay. Wherever we do have plots, it's not like they're all really productive or really unproductive. It's sort of, they're all kind of mixed in together wherever we have these lodgepole plots. Okay, and again, 1990s to 2000s, if we look at a 4-state average, so ignoring Wyoming, because that was a slightly different time period, increase in total biomass, pretty big increase in dead, almost double, and a decrease in live. I'm going to zoom down here to Wyoming. This was the early 1990s to the late 1990s. Big increases there, a lot of growth going on. This is before some of the bigger fires and really the onset of the mountain pine beetle epidemic. Colorado and Utah actually saw increases in the live and total biomass, and Idaho and Montana started showing a shift from live to dead biomass there. Okay, and again, this graph shows the mean annual change by year of the second measurement period. Up until 2005, the change in live and dead biomass tracks each other pretty well. And then in 2006, the increase in dead biomass and the decrease in live biomass really gets big. And by the end of the measurement period in 2009, the change in dead has a greater magnitude than the change in live, sort of a double whammy. So we'll probably continue to see that. Okay, and this is the distribution of aspen plots. We actually had aspen plots in each state, but not many of them except in Colorado, Utah, and scattered a little bit in Idaho and Montana. And again, kind of ignoring Wyoming for the time being, the regional trend was an increase in total biomass. Live didn't change a lot, and an increase in dead biomass. Colorado and Utah didn't really see any change in live biomass, but in Idaho and Montana, there were big decreases in live, another shift to dead biomass there, and a total decrease as well. So to summarize, the specific forest type trends, pinyon juniper biomass increased overall, and that was true in every state for statewide averages except for Utah, where we saw a slight decrease. And again, that decrease tended to occur on private lands, BLM, and then state and local government lands. The increase that we saw in live PJ biomass had a mean annual average of 1/10 of a ton per acre per year. Lodgepole increased in Colorado and Utah. Big shift from live to dead in Idaho and Montana, as we saw some disturbances taking hold there. Aspen decreased in Idaho and Montana, both total and live, and then slight increases in the total biomass in Utah and Colorado. And again, I want to emphasize that I sort of hand-picked these forest types. They're things I thought people might be interested in. We can definitely look more specifically at a state of interest, a forest type of interest within different elevation zones or ownership categories. We'd be here a long time if I tried to present everything I thought was interesting, though. So, okay, now really big picture trends. This is like the macro trend is across the interior West, total standing biomass is increased, dead biomass is increased, and live biomass either hasn't changed or has decreased, sort of depending on the state. So stuff is accumulating. And again, the take-home message, if you're trying to create large budgets for biomass or carbon, greenhouse gases, and what's being stored as standing wood on the forest, you need to look at both the live and dead components. Otherwise, you could draw some erroneous conclusions about what's going on. So as I mentioned, beginning in 2000, FIA began a new sample design. We're going to be revisiting each of our more than 30,000 plots every 10 years. We do 10% per year. We're also working on improving the way we calculate biomass, trying to move toward this, one definition, one biomass, both by improving individual tree calculations and then also being able to account for understory and forest floor biomass. We're also excited about projects like what Brent talked about this morning with LiDAR, other remote sensing products that can be combined with FIA data to produce continuous biomass maps across the landscape. Finally, one last plug. If there's any burning question you're really dying to know about a certain state, forest type, subpopulation, please contact me. As Justin said, we're also having stakeholder meetings within the next year or so for Arizona, New Mexico, and Utah, and you can contact me about those as well, and we can make sure that you get information about them. So thanks for your time. I'd be happy to take any questions or comments.